Did you ever imagine that your daily plastic bottle could become the clothes you wear? This remarkable process is part of a growing movement to reduce plastic waste and transform the textile industry.
Only betting on this, expanding our capacities, thinking that the future is going to be sustainable fashion, and we want to be well placed when that way.
Through advanced recycling technologies and innovative manufacturing processes, discarded plastic bottles are being converted into a wide range of clothing items, from casual wear to athletic gear. But how does this process actually work? Let's get into it. Sri Ranga Polymers, based in Tamil Nadu, India, processes about 1.5 million plastic bottles daily to create fibers, yarns, and textiles. Established in 2008 and led by K. Sankar and his son, Senthil, the company supports their sustainable fashion brand Ecoline, which produces jackets, blazers, and other garments made from recycled bottles. For example, each Ecoline t-shirt requires around 8 bottles, while a blazer uses approximately 30. Recently, Sri Ranga Polymers invested about $12 million in a new recycling facility in Karur, Tamil Nadu, to expand production capacity. This facility employs advanced recycling technologies to convert waste bottles into high-quality polyester fibers. The company currently generates an annual revenue of approximately $14 million, highlighting the financial and environmental impact of sustainable practices within India's textile sector. Is Sri Ranga Polymers the only company embracing this technology? Well, stick around and watch the video until the end to discover more exciting initiatives making waves in the industry.
In 2023, the family received a huge boost after India's Prime Minister, Narendra Modi, wore one of their vests, known as a sadri.
I was literally in tears. My product is worn by a Prime Minister of the country. Something wonderful.
The facility implements a multi-step process to maximize resource efficiency and minimize environmental impact. The recycling process begins with the collection of polyethylene terephthalate or PET bottles from various collection points. The material quality is assessed upon arrival to ensure only usable plastics are processed. Once the plastic arrives at the facility, it undergoes sorting, separating PET bottles from non-recyclable materials. The bottles are further sorted by color to maintain a consistent appearance in the final product, since mixed color plastics can affect the dyeing and finish of recycled polyester. After sorting, the bottles are intensively washed using a specialized friction washer that eliminates contaminants such as labels, adhesives, and residual liquids. This thorough cleaning ensures the quality of the final product and minimizes impurities. The clean PET bottles are then fed into high-speed shredders, transforming them into uniform flakes, an essential intermediate product for polyester fiber production. The flakes are rinsed thoroughly to remove any remaining contaminants. Melting and extrusion are the next stages in plastic recycling, transforming collected plastic waste into reusable raw materials. The process begins by heating the plastic to a precise melting point in a specially designed extruder. The required temperature varies depending on the plastic type. For example, polyethylene melts at around 120 to 130 degrees Celsius, while polypropylene requires 160 to 170 degrees Celsius. Thermoplastics are well suited to this process since they can be melted and resolidified multiple times without significant degradation. A rotating screw within the extruder mixes the melted plastic to ensure uniform consistency. This step typically uses either a single screw or a twin screw extruder, with twin screw models providing better mixing for diverse plastic types. To achieve consistent product quality, the plastic is often blended with master batch colorants during this stage. Once the plastic reaches a homogeneous state, the material is pushed through a die, which shapes it into plastic sheets, filaments, and other forms. The design of the die determines the final product's form, while the screw's length to diameter ratio, usually 25:1, plays a crucial role in mixing and output efficiency. Higher ratios, such as 32:1 or 40:1, improve mixing but require more energy. After extrusion, the plastic material is rapidly cooled in a water bath or with air to solidify it. Once cooled, it is cut into small pellets or granules known as regrind or regranulate. which serve as a feedstock for injection molding or further extrusion processes. These pellets are widely used to manufacture products such as pipes, containers, and textile fibers, depending on the purity and composition. During the fiber spinning stage, specialized equipment transforms melted polyester pellets into thin, high-quality fibers. This stage involves several high-tech machines that ensure the production of strong, flexible, and durable fibers, suitable for various applications, from clothing to industrial textiles. The process begins by melting polyester pellets, which are then funneled into a spinner net, a device similar to a shower head with numerous small holes. As the molten polymer is forced through these holes, it forms continuous filaments. These initial fibers are semi-solid and must be cooled to stabilize their structure before further processing. The fibers pass through a cooling chamber where they solidify. The step provides the basic structure of each filament and ensures uniformity. Cooling drums or air-cooled systems are typically used during this stage to achieve consistent shape and dimension. Next, the filaments move to high-speed draw frames, which stretch and align the fibers. This stage, known as drawing, is critical because it orients the molecular chains within the fiber, significantly increasing tensile strength and flexibility. The draw frames apply precise amounts of tension and heat, lengthening the fibers, sometimes doubling or tripling their length. This alignment enhances the fiber's resilience, making them more durable for use in textiles and other applications. The final processing and quality control stages ensure that the polyester fibers meet industry standards and specifications. After drawing and spinning, the fibers undergo various finishing processes, such as heat setting and texturizing, to stabilize their structure and enhance their properties. During heat setting, fibers are exposed to temperatures above their glass transition point to lock in desirable properties such as dimensional stability, shrink resistance, and improved dye affinity. This process also aligns the polyester polymer chains, resulting in a smoother and more uniform fiber structure. Equipment used for heat setting includes stentors and heat rollers, which uniformly apply the necessary temperature to stabilize the fibers. Quality control involves testing the fiber's mechanical and chemical properties. Key assessments include measuring fiber tenacity or strength, elasticity, and uniformity, as well as evaluating color fastness, dye absorption, and thermal stability. Differential scanning colorimetry, or DSC, is often used to verify the fiber's crystallinity and thermal properties by analyzing heat flow and transitions during testing. This helps detect inconsistencies in the polymer matrix that could affect fiber performance. Recycled polyester, known as rPET, offers numerous environmental and functional advantages. It serves as a sustainable alternative to virgin polyester, reducing greenhouse gas emissions and conserving resources. Producing rPET requires up to 59% less energy and 32% less water than traditional polyester, resulting in a much smaller carbon footprint. Despite being recycled, rPET retains the desirable qualities of virgin polyester, such as durability, moisture wicking, and versatility. These characteristics make it ideal for various applications. Additionally, rPET maintains its integrity through multiple recycling cycles, allowing manufacturers to reprocess it continuously. However, its current market price remains higher than conventional polyester due to limited infrastructure and demand, although this gap is expected to narrow as more brands adopt sustainable practices. Several companies have embraced this technology, contributing to a more sustainable textile industry.
In January 2020, Biffa opened its state-of-the-art PET plastic bottle recycling facility in Seaham, County Durham. This £27.5 million investment forms a key part of Biffa's sustainability strategy and helps us to deliver on our continued drive towards a true circular economy in plastics.
Global brands like Patagonia, Nike, and Adidas have incorporated rPET into their products for years. Patagonia, a pioneer in this field, transforms plastic bottles into fleece and other apparel, promoting environmental consciousness across the industry. H&M and Decathlon are also making strides. Decathlon has partnered with Recycleit, a French startup specializing in recycling complex textile materials, to develop circular solutions by recovering various plastics from textile waste. A demonstrator facility is expected to launch by 2025. High-tech solutions from companies like Evernew and Eastman are also transforming recycling processes. Evernew's patented NewCycle technology re-engineers discarded fabrics into polyester-like materials without compromising durability. Eastman's carbon renewal technology employs molecular recycling to convert polyester waste back into its plastic components, creating an almost endless recycling loop. Swimwear brands like Kitty and Vibe, along with Ellie Evans, use rPET in their collections, offering vibrant designs while reducing reliance on virgin plastics. If you enjoyed this video, check out other videos on our channel.